Okay, hello everyone. This is the NXTP router. The router is one of the main modules off-chain components in the architecture. It's in charge of monitoring the transaction manager contracts for transactions that are prepared with it, and then preparing on the receiving chain if it has sufficient liquidity, and listening for auction messages to handle auction responses and publish bids for users to accept. So the main file, the main entry point is the index. The index sets up a basic Fastify server. We're not really using the HTTP components that much, but in the future we might want some debug component or debug endpoints, as well as like configuration getters and things like that. So the very first thing that happens is get config. So the config file is set up very similar to how we set it up in Vector. I kind of like the way that this architecture worked. So basically what we do is we set up some schemas that we can validate how the config schema is. So it's an easy way to make sure that all of the keys are present and in the structure that we expect it to be. So we have a function called getEnvConfig. So this config will first check for a config file. So you can use this environment variable called NXTP config file, which will point at a file on the local file system to read as configuration. If this config variable does not exist, then it will look at a default in the same directory called config.json. If it finds it, it will parse it. And if it doesn't find it, then it will try and get keys from this NXTP config variable. So you can insert the whole config as like a stringified JSON in an environment variable called NXTP config. And then past this, you can actually override individual environment variables with each key. So then what we do is we parse out each bit of the config and we check if there is an environment variable. And if there is an environment variable, we use that. Otherwise, we use the config.json. Otherwise, we revert to the config file. So the way this works is you can actually have like a config file and a config variable and an individual like configs for the individual keys. So that way you can kind of override things in a pretty cool hierarchy, where the environment variables, the individual ones, take the ultimate precedence over the config variable, and then at the end is the config file. So this is all extracted and validated. Oh, and then one thing is we add contract deployments from the contract deployments, which are part of the package that we publish. So if our overrides are not specified, we don't expect like router operators to specify the actual contract addresses. They can if they want to, but if they don't, then it will just use our default contract deployments, which are published of open source, of course, so they're all fully validatable. Also, minimum gas requirements, we added that as like a per chain configuration. So this will be checked against when the router responds to messaging requests. So all of this gets validated and then throws an error if it's not, if it doesn't match the provided schema. Then we set up a wallet based on the config mnemonic, a logger, messaging service. So this is a messaging service. It's basically very similar to all the messaging services we used in Vector, but it basically is like an interface to the NATS protocol itself. Then we set up subgraph class, which is the interaction with the subgraph, which is what we use to monitor the contracts. The subgraphs are nice because we don't have to constantly pull contracts or listen to events, which are pretty expensive on the RPC. Subgraphs basically create like an up-to-date view based on, and that uses contract events as basically an event stream. Then we create an instance of transaction service, which is our like our standalone module for sending transactions to chain. Then we have transaction manager, which is, we'll go through all these classes in detail later, but transaction manager is basically a wrapper class for the transaction manager contract, which makes use of the more generic transaction service. Then we create a handler, which is basically a container, which uses like a dependency injection module that holds all of these classes. And that is basically the main class. Then down here, basically we have some schemas that we're using for the HTTP. When I said that we don't use the HTTP stuff, we actually do for a couple of requests, which are very minor and we can go through right now. Then server add hook. So this is a hook on ready. So this will just like hook back and let us run some async computation when the server actually comes up before everything starts up. So we connect messaging, set up listeners, and basically validate our configuration there. Then this is where we actually define our router endpoints. So we have a ping endpoint, we have a config endpoint, which right now just returns a signer address. We can figure out how to extend this and add more stuff to the config when we need to. Then remove liquidity is another big one. So on the contracts, the router is the only one that can remove its own liquidity. So that has to be like an accessible external interface that can be called. This is not external as in like external to the world, it's just external to the router. So whoever is running the router in their trusted execution environment, they will be able to call this endpoint. And the idea is the router should never be exposed on like public HTTP. Okay, so the first thing we can jump into is basically the handler, which is like the top level function. This is more or less like the entry point of how all the events that the router reacts to are handled. So the first method is handle new auction, which takes data in the form of an auction payload. So this is all the information that is this is basically what gets actually, sorry, before I get into this file, we should get into the listener, because the listener is how everything is hooked up. So the listener takes an instance of the handler plus the other helper classes, and then it hooks everything up. So the listener is what actually will take the auction request, the message, the published message of the auction request, and hook up the handle new auction method. So when the messaging service, when the subscription, so it sets us up a subscription. So every time it gets an auction request, it will call this handle new auction method. And handle new auction, now we can go back to that since we know how this method is called. And so we destructure all of the data here. A to-do here is to actually validate the structure of this data. Since this is coming in externally, we should always make sure that this is correct data. So then we calculate the amount received. So right now we basically just do something very simple, and we calculate an exchange amount based on a hard-coded swap rate, which is 50 basis points. So we basically will multiply the incoming amount times this hard-coded swap rate, and we will get the amount that is received on the user side. Then we will call get config. We make sure we call get config in all these functions because of how we test. So when we test, we want to actually mock out the config itself. So in order to do that, we can't just get configs from like a global state. We actually have to get it within the function itself. So then we call the result, we get the asset balance. I'll go over this at a high level, then we can dive in earlier. So we're using this pattern called never throw, which basically lets you chain result. It uses this special result type that contains basically like a functional way to either operate on the result inside of it or an error if it's an error type. So it forces you to basically handle all possible error cases and have like nice like typed way interfaces for doing it. So we'll see the way it works here. So basically we call this dot subgraph dot get asset balance. So this will get the actual asset balance from the subgraph. And we can do this from the subgraph instead of reading from the contract because all of the liquidity changes for the router are driven by events. So just using the event stream of the contract lets you recreate a perfectly accurate picture of the router's liquidity, which is really cool because now we don't have to read the contract. We can just go straight to the subgraph.
So sorry to jump in here, but is this going to stay the same for when the shares are added?
No,
Because
so
the shares adding is what they're going to actually like be auditing.
Okay. So then, yeah, we'll have to say that this is a placeholder here. Right now, we can use a subgraph to get the asset balance and all the available liquidity, but when we move to our shares-based model, we are not going to be able to do that, and we're going to have to probably call to the contract on every call. Maybe we can do some kind of caching or something.
Right.
Yeah. So
also, this wouldn't also work on like is the liquidity updated when transactions are prepared?
Yep.
And when they're fulfilled?
Yep.
Oh, it
absolutely.
is?
Yeah.
Sick.
It follows all the whole. Yeah, we should probably go through the subgraph module too separately, but we can do that.
Yeah.
We can do that separately, I think.
Okay.
But yeah,
Okay.
I mean, it matches the full contract logic because we wanted to make it so the liquidity reflects. So it's updated the same way the contract updates it within the subgraph.
Nice.
So yeah, so then if we don't have enough liquidity, we return basically an error type, which is like a custom constructed error, which follows a nice little structure here. So it says not enough available liquidity. And then we do some other checks. So we check the config, we check if we have providers for the sending and receiving chain. Then we do this thing called combine. So this is from the never throw library. It's basically like a promise.all, but you can do promise.all and basically get custom errors out by using this from promise thing. So from promise turns a promise because the TX service stuff throws errors. So it's like basically an unsafe function. So what we can do is we can use result async dot from promise to turn it into like a safe function. Then we provide like a callback function that gets called in the case of an error. So this will handle the internal like try catching, and then it will spit out this error if it fails. And then we can take this error, we can transform it again to one of our nice errors. So we do this for the sending chain balance and the receiving chain balance to get the balance of the signer address on both chains. Then we call and then, so that will basically map this to, or that will basically attach a new operation that this will only happen on the like happy case. On the failure cases get handled outside of this, or failure cases basically don't, basically if it throws an error, it doesn't go into this and then. That's what I'm trying to say. So then basically we do these checks against the config min gas. So we had a min gas, we have this hard coded, but this can also be specified per chain. So if we don't have enough gas on either of the chains, we don't want to respond to the auction. So then we throw another handler error saying not enough gas. And then finally we say, if all of this works, of course we can attach more validation here. I think we do need to attach more validation. I think one of the things you mentioned, Lane, is allowed swap. So we should think about the best way to put that in here. Right now, it's basically just it's checking its liquidity and it's calculating a 1-to-1 swap rate. So it's basically saying if it has enough liquidity, it's basically trusting the like sender receiver asset combination it's getting in the auction response, which it absolutely should not. It should be basically checking against like an array of swaps that it wants to complete, right?
Right.
So we should say to do validate sending receiving asset combo against whitelist from config.
It should also probably like check an oversubscribed ratio, like in the case where it just gets a ton of auctions. Like obviously there's like going to be a lag and they may not win all of them, but like it shouldn't bid if it's oversubscribed
Yeah,
itself.
absolutely. So we need to like cache, we need to cache all of these auction responses, and we need to like basically decrement the available liquidity that it has. So it shouldn't just be looking on chain, it should be looking on chain minus all the stuff that it has already like put out.
Right. But it shouldn't assume, like, it shouldn't really assume it's going to win 100% of the auctions. But whatever.
Right, but
For now,
it
it
is
can.
liable to do that, right? So I think it should probably, that's why I was thinking maybe we can use like Redis for it, because we can like set an expiry on the keys pretty easily in Redis. So then you can basically just use that same expiry as the expiry of the auction, and
Yeah.
use that to, yeah, basically use that to
Yeah.
calculate your liquidity. So I'll add another
Nice.
to-do for that. Use cache auction responses. Sorry, one sec. Okay, so then once all these validations are complete, sorry, go ahead.
Oh, I was just going to say, like, can you explain to me a bit, like, is it going to run an auction each time the user refreshes the UI? Because then we should probably not, like, we should probably do some type of oversubscribed situation, like some allowable percentage over the total.
Yeah, well, I guess I don't know how their UI works. In our UI, we made a button for it, but I think their UI
Right.
will do it when you like type, like on type. So like if you type
Oh,
in a
damn.
number, then it'll start an auction after some like short delay.
Okay, so we may have
But
to
yeah,
add some more considerations to like how exactly it's calculating the available liquidity.
yeah. How UI calls it. Yeah, I mean, that's kind of a lot of, that's some of the things we were thinking about when we first started this, is like, how do you like estimate a fee almost without like committing to an auction? It's
Right.
difficult.
Yeah. We should maybe have like a dry run auction situation where it's like you don't return a signed bid, but you just return a bid so you can get an idea.
Yeah, that might be a good idea, but does it matter if somebody else responds? Not really, I guess.
Yeah,
Yeah.
I mean, it depends on how it's being called, right? But like it could cause problems if you're constantly sending out signed bids, because even like in a malicious way, if the user's like collecting all of those and then gonna like slash you because you didn't put it on chain, or they like store them all or something weird like that. I don't know. It could get funky when you add in slashing. For now, it's probably not that big of a deal, but if we're, depending on how we calculate available liquidity based on these like auction responses, it may become.
Yeah, totally. Okay. I guess. So then we have to consider all that, but assuming we get to this point where we validate everything is good and then we're ready to send the auction back, we create the bid, get the bid expiry. So get the bid expiry right now, we'll just add 5 minutes to the bid, to the current time to get the expiry. And then we'll generate the bid. Then we will call this other function to sign the auction bid. Then when we sign the auction bid, we get a signature, and then we publish the response here. And cool. Yep. So now we got to the end. So this is the cool part about never throw, because now we can just check is okay at the end. And if it's okay, then we say, yep, it worked, and log it. We should also update the metrics here. And otherwise, we can just log an error because if we get some kind of error along the way, that means we're not trying to send the message back, so it doesn't matter. We don't need to do anything else. We can just like not respond. Cool. So handle meta transaction requests. So this is a little different. I think we should probably come back to this function, but we can go to the other function. So handle sender prepare. So we can again look at the listener to see how this is hooked up. So subgraph has an interface where you can attach to subgraph events. We'll go through how that works later, but we can assume that the subgraph will tell us when there is a sender transaction prepared event that we need to handle. So then we will go to this handle sender prepare function. So for the purpose of handle sender prepare is that the router should mirror the data to the receiver chain. So same thing, we will log at the start, generate a unique method ID, and then we will destructure the data to do some of the input validation. So validate the structure of this data. This is coming straight from the contract, so it really should not be. So it should be right, but there are things we want to validate. Like I believe what we want to validate is things like the bid, so the auction bid. So to do, I think I need to already know some of the things we need to do here. Decode bid and check bid expiry. So if the bid is already expired, we probably want to just cancel. If expired, cancel. Since the router is the receiver on this side, it can cancel the transactions. So if it sees that it's been done, then it wants to cancel it. Maybe it should also check amount against the bid that it made.
Yeah, it should also check its signature on the bid, because like nothing is going to be,
Oh, yeah,
nothing about
absolutely.
the bid or the bid signature is validated on chain.
Yep. To do, what if there's never a fulfill? Where does receiver cancellation get handled? Receiver cancellation gets handled elsewhere. Yeah, that's not here. What needs to be validated here is this necessary assumption that users only sending stuff that makes sense as possible, otherwise they're losing gas costs. Yeah, we still want to check some of these things up here. So next, prepare the outbound data, must have all this data. I don't think we need this comment anymore because now we kind of know. Amount and expiry need to be modified. So amount and expiry need to be modified because this is where the router takes its fees. So the router needs to modify the amount to take its fees. The expiry needs to be modified because the receiver side always needs to be canceled before the sender side, because that is one of the like properties of the security of the protocol in general. So we don't need these nodes because they're going to get out of date. The types all say what we need to do. So now we will call to the transaction manager to prepare the transaction once we have all the relevant data. So we get all the data from the event, pass it back to the transaction manager on the receiving chain with the new amount and the new expiry based on what we calculate. Mutate amount also right now, like I said, it uses a hard-coded swap rate, but eventually we want that swap rate to come from our like bonding curve virtual AMM mechanism, and also we want to be reimbursed for any gas fees that we are paying for this stuff. So the user is going to take the burden of the gas fees. So we check the result on that. If the result is okay, then we prepare the transaction. And then if the result is not okay, that means the transaction failed to send to chain. So what we do is we check something here. So we check if the error message includes this like special error code, which means that the transaction was already prepared. That means that we basically like double send a prepared transaction, and since it's idempotent on chain, it's not going to work because the digest already exists with the exact same transaction ID and data. So in that case, we don't want to do anything. But if it failed for some other reason, we might want to cancel. So I actually commented this out at the moment because we are seeing issues still right now where like transaction service stuff is like kind of flakily erroring but actually succeeding. So in that case, it's extremely dangerous to cancel because we don't want to cancel if the prepare went through on the other side, because that basically is giving the user money. So for now, this is commented out, but at some point we probably want to like cancel the cancel on behalf of the user, because this is just kind of being nice to the user and canceling for them because you're saying like they can't get their funds, so they don't have to wait through the expiry period. Cool. Okay, so next thing that's hooked up is receiver fulfill. Actually, we can do the next part of the flow, which is the meta transaction. So now in the actual full protocol flow, at this point, the transaction is prepared on the receiver side. So the receiver will get notification that transaction is prepared on the receiver side, and then it will broadcast, it will sign the payload, and then it will broadcast it to the network of meta transaction relayers, which the routers already are. The cool thing here is anybody can send this transaction. So we decided to make the user experience a little better and not require the users to actually make the transaction themselves and like have gas on the receiving chain. So what we do is we have this meta transaction. So anybody who gets this meta transaction request from the user can actually submit it themselves, and they can collect a fee for doing that. So we are listening for a message that has a meta transaction request, and then we will call this handle meta transaction request on that. So same handler setup, we have some data. I left the types of this a little open-ended, so that can have like a mapped type with a payload that can be different types of meta transactions. I don't know if we'll need any other types of meta transactions. Right now, we just have one called fulfill, but we could potentially add other meta transactions that our routers can fulfill for users. So if the data, we'll check if the data type is fulfilled, and then if it is fulfilled, then we will submit the TX on chain. So we send the transaction manager fulfill on chain using the data that is part of the payload. And then if that all worked, then we relay the transaction and we submit the response back just so the user can like see what their like the transaction stuff that got sent to them. One thing here is that this is not actually going to be sent until the transaction is confirmed. So the problem with that is the user might be waiting around for a while and not know what's happening to their transaction until they get like a response. So at some point we might want to do like a first level, like, you know, your transaction is being handled, where we can get some kind of like public, some kind of identifier from the transaction manager being like, here, it's in progress. And then we can like submit a follow-up saying that, okay, here, I got mine. Okay, so then we have or else. So this is like a handler which will handle an error in this process. So if this errors, then it will create a new error and then publish a meta transaction response. So it will tell the user basically it wasn't able to submit it, just so the user has some information. And then if this result is okay, it's cool. Otherwise, it errors. Cool. And then the last thing is, well, not the last thing, but the last handler here is the receiver fulfill. So same thing, it's listening to the subgraph events for receiver fulfill. Receiver fulfill is nice and short. All it does is just send a fulfill. So the purpose of this receiver fulfill handler is when the receiver side gets fulfilled, that means the user has broadcast their signature, some meta transaction relayer has picked it up and fulfilled it on the receiver side, which means we have all the info to unlock the sender side and take our money back. So we have locked up funds on the receiver side. We basically like fronted money, and then that is locked up until the user gives us their signature to unlock the funds on the sender side. So now at this point, we've gotten the receiver fulfill. So now we want to unlock the sender side and get our liquidity back. One thing, big thing that's missing is like, we need a cancellation handler. It will look very similar to this one, which is nice. So it'll just basically pass on it the cancellation request or signature to the other side.
This is the meta transaction relayer, right?
This is not the meta transaction relayer. No.
Okay.
So this could be done with the meta transaction, but we're assuming like nobody really cares and the router is just going to fulfill it themselves. I think we need some kind of like signature situation to you put a fee to it. So somehow this guy would need to broadcast a signature anyways, I think.
I don't know. I don't think so. Why would it need to broadcast a signature?
Well, how would the relayer collect a fee?
The fee is sent from the amount on the contract. So like if it's a router relayer, no, they don't get any fees, so there's no incentive. But if it's a user relayer, it's just like sent directly to whatever address.
Right, that's what I meant, a router relayer. So the router relayer, there is no like router relayer because nobody else is going to send the transaction because there's nothing in it for them. So the router basically needs to take care of its own fulfills.
Yep. And then so this cancel handler is to like, if the user cancels on the receiver chain, then you also cancel the sender chain, right?
Yep.
Okay, exactly. My bad.
So yeah, actually, do we need to do that? How badly do we need to do that?
I mean, if you're being shisty, you could always just wait and be like, okay, well then I'm not going to cancel it anyways, and wait for the user to broadcast to the relayer network so you get a fee for canceling it because technically they've already released your liquidity. But that's like not that nice.
Right.
For you to do. That is, it would be more beneficial.
Yeah. Okay. So I guess, yeah, we can kind of come back to that. I don't know if we need that right now anyways, because, you know, if they cancel, they can wait. Well, presumably they would cancel because something was wrong with the transfer because you prepared the transfer for them and then they canceled because maybe you didn't prepare the right amount or something like that. So I think it would get into like slashing condition type stuff anyway.
Right. And like in theory, like holding up the sender side cancel or like not like forcing the user's funds to be locked would also be slashable in some way.
Right, exactly. Okay, cool. We're running out of time. Should we like re-up this meeting? We have like a few more, probably like 15 minutes or so. Shouldn't take that much longer.
Yeah, we should probably just re-up it.
Okay, I'll just stop it and we could do a part 2. Okay, talk to you guys soon.
All right, bye. The great news is it's recorded. But it does sound like we're finding some good things, so.
Yeah, absolutely. These are always very good to do, I think, in general. Okay, so now basically, now we've covered that. So the main other thing is the subgraph class. So that is how we listen to the subgraph. Again, just to reiterate, the subgraph is like basically a database that allows like a queryable view of smart contract data. So you can define a mapping to map events to entities. So basically you can like create these long-standing entities that get updated on every event that happens on the chain. And then the subgraph basically crunches through all the blocks on chain and then creates your entity basically, which is like a fully up-to-date view of what's happening on the chain driven by events. So it's pretty cool little structure here. So the way this works is it has this subgraph class. We can go through some of the stuff, but this is just basically like setup types and helpers for the class itself and EVTs that track the events themselves. So basically what happens is this takes in a chain config, which is your chains, and it's a mapping of your chains to subgraph, which is the URL of the subgraph. Right now we're using hosted subgraphs, but eventually the router will probably have to run its own graph nodes and run point to local subgraphs. It takes in a router address because it needs that for some of the queries, and loggers and poll intervals. So the way it works is it's polling the subgraph on every poll interval, and we do some cool things to like debounce this that I'll show you later, but basically it's kind of guaranteed that it's only going to get one event for it's only going to like call the handlers once for each event. So it starts off by running this thing called a subgraph loop. So basically there's only 3 categories that the router cares about, which are sender prepared, receiver fulfilled, and receiver canceled. Basically, it only cares about them also in the context of the way that the router cares about these events. So a sender prepared event for the router is a sender transaction which has not been prepared on the receiver side, because you could have like double of these events. So if you just consider sender prepared, any sender prepared, then you could have overlapping events where sender prepared is also a receiver fulfilled, is also like a receiver canceled. You don't want that. So specifically, we only care about sender prepared events in the context where there are sender transactions which have not been prepared on the receiver side, i.e. they have never existed. Receiver fulfilled are receiver fulfilled transactions which have a corresponding sender transaction in the prepared status. So if it's fulfilled on both sides, because the subgraph, okay, so the reason we're doing this is because the subgraph is like a structure which is constantly like it's a fully persistent database, right? It's never going to delete entries. And also it doesn't know, one chain of the subgraph does not know about the other chain of the subgraph. So you can't be like, oh, if it's fulfilled on both sides, change the status, because it doesn't know what the other side is. So basically you kind of have to track it like individually like this, and basically tie the 2 subgraphs together from the sending and the receiving chain to determine like an accurate status. Does that make sense to you guys?
Yes.
Cool. And canceled. So basically we can do everything by checking the sender side prepared transactions. So we check sender prepared, then we check on the corresponding receiver side if the receiver side has been is what status the receiver side is in. If it's prepared, it's sender prepared. If it's not prepared, it's sender prepared. If it's fulfilled, then it's receiver fulfilled. If it's canceled, because like the other combinations we don't care about. If it's sender prepared and receiver prepared, that means we already prepared it, so we don't want to like get an event for it. Cool. So basically, in this loop, we set an interval, and in each interval, so we do this thing to flush. I'll get into flushing later. But basically every 20 loop iterations, we need to flush the EVT's context. So we get all sender prepared transactions. So we will get all the transactions that are in the sender prepared status. So Marcus, I think a little bit ago, you correctly noticed that it wasn't getting try catch. So if any of these calls are failing, they were like blowing up the unhandled promise stuff. So yeah, we have to wrap this query in a try catch. So we get all the sender transactions, and then for all the sender transactions, we basically create a list of transaction IDs for each chain. So we get all the transactions for one chain. So this is running on each chain, basically. This interval is running on each chain in the config. So all the different chains are running this loop individually. And then for each chain, we will actually set an interval to get all the sender transactions. Then from all the sender transactions, we'll create a list of all the receiver transactions. So if you can assume it's like A to B, A to C, A to C, A to B, we need like, we need the list of all the transactions there to get. And then we query all the transactions, all the receiver side transactions that are corresponding to the sender side transactions. Then we look at all the sender prepared transactions, find the receiver transaction. If there is no receiver transaction, like we said, we will post to the EVT that it is a sender prepared transaction. If the corresponding side is fulfilled, that means we have a sender prepared, receiver, or sender is prepared, receiver is fulfilled. That means we need to do something. We need to fulfill the receiver side, the sender side ASAP to get our liquidity back. So that means we want to post to that event. So we post both the sender event of the sender event, which is the prepare event, and the receiver event, which is the received event. And if it is canceled, same thing, we want to post to that EVT. And then we have a couple more helper events just to get transaction from chain. So what that does, it just takes the transaction by ID from a chain, and then it will convert it into like the proper like actual like event-based type. So the subgraph has like its own type mapping that is not really fully related to the contract. So we just wanted to like map it back to the contracts. This is all red because I was on a previous branch that changed some of these types. Then also we have get asset balance. So I showed before that we were getting asset balance from the subgraph. We're probably not going to be able to do that anymore with the shares thing. But we had a way to get the asset balance directly. So this is where the flush stuff comes into play. So we attach and using the EVT. So EVT is basically like this container that's an event emitter container that has like a bunch more functionality on top of just like a events. I was talking to you before about using observable, but I put an issue in an EVT and the guy like implemented it like that day, which was super dope. He like copied the exact observable interface and he put in this distinct operator. So the thing with the subgraphs is if we're polling it and it's in the sender prepared status, and then we on the next poll, because we're like in the middle of sending transaction, we don't want it to be like sender prepared again. So we only want to send it once for that. So what we do is we create like this distinct filter. So it's only going to send the sender prepared event for one transaction ID one time. And of course, if it's going to be constantly keeping track of all the IDs it's ever sent, this is going to like slow down over time. So that's why we have that flush thing up here. So that's where the flush comes into play. So every 20 loop iterations, it's going to, this is an arbitrary number. We can change this to whatever. It's going to flush the flush context. So this means there is a condition where if the sender prepare happens, the event goes out, then it flushes the context. Then on the next loop iteration, it's going to see that it's never sent that. So it's going to like send it again. So there are some cases, but I think that's an okay trade-off to make because nothing really hurts if you send the transaction twice. I mean, first of all, it should revert in the estimate gas, so it shouldn't even go to chain. But if it does somehow go to chain, it's just going to revert on chain and it's going to, basically just spend a little bit of gas, but it's okay. I mean, we can also like increase this interval to like reduce the frequency of that happening. Yeah. So that's that. And then these queries, basically the subgraph uses this SDK, which is generated from these GraphQL queries and our schema directly. So we define the queries separately in this special file. So we can define things like get sender transactions, which can put in a full GraphQL query that's based on some of these variables that we pass in. So we have get sender transactions, get receiver transactions, get transaction by ID, and get transactions by ID. So we're trying to optimize the queries as much as possible. So when we get that list of transaction IDs on the receiver side, we query them all at the same time instead of querying for each one individually. So per chain, we can query all the transaction IDs. Yep, that's that. And then one of the other helper classes we didn't go through is the transaction manager class. This is quite simple. Basically what it does is it takes a TX service and it takes the transaction manager interface and it takes the config and it basically translates the prepare, fulfill, cancel, all those functions into like on-chain calls for a particular chain ID. So the callers do not need to know where the transaction managers live on chain, what the address is. They just need to pass in the chain IDs and this thing will go and look them up. And then since the transaction service is generic, we do all the data encoding here. So we encode the data using the transaction manager interface, and then we like post that data to the transaction service, which calls send TX using the data that was encoded. Throws appropriate errors using this never throw result async pattern. So everyone that calls this is forced to handle the errors that may come out.
Never
cool.
throw library is sick.
Yeah, it is sick. It's funny because we like tried to make it ourselves with vector and like it kind of worked, but it was annoying because you have to like basically unwrap it every time you use it. And like this one is basically like the main difference is you don't have to unwrap it. You can basically like keep going in the case where it is a proper result and only handle the error case at the very end, which is how we want to do it.
Yeah, it's nice.
Yeah, apparently he copied it from Rust, right?
Yeah, exactly. It's like inspired by Rust. Like Rust and all these functional programming languages do like this whole pattern. This is like a big thing in that world. Cool. So I think that about wraps it up for the router. So the main to-dos, I believe, were some of the things we discussed about the auction validation. Sorry, auction validation is up here. So auction validation, we need to validate some of the like combos and cache the auction responses with consideration to how the UI is going to call it and how often it's going to prep it. Oh, also to do add dry run. So I like that idea of the dry run auction where you can just get like a response and a estimate. Yeah, so that's about it. I think we did go through all the files, so that's cool. Anything else anyone needs to know?
No, I don't think so. What's the test coverage look like?
Test coverage is pretty bad right now. We're mainly just testing the handler. So the handler, at least all the functions do have tests. So we're testing basically the calls, but it's a unit test, so it's mocking out all the other classes that go into it.
Right.
But yeah, we're working on that.
Cool. What do you, like? What are do you think the main changes are going to be for when we shift to the shares stuff? Seems like it'll mostly be around liquidity on prepare.
Yeah, I believe the
but
like
everything else should be the
biggest,
same.
yeah, the biggest one is, which I also really don't like, is the fact that we have to call the contract to get an updated view of the shares. Is there a way we can like cache that? Or is that unsafe? I mean, because like, you know, if we're getting 800 transactions an hour, like she's gonna be constantly like checking its shares and amounts and stuff. Maybe we don't need to do
I mean,
that every.
you can use the subgraph to get an accurate amount, like view of the shares that the router has. Or you should be able to, we should at least
Right.
build it so that you're able to do that. But it's just the amount that that's worth that may be a bit of a pain.
So does it matter, I guess? Oh, well, because we could make it so the user has to convert the amount to shares, right? Can the
Yeah.
user do that? Or if
Yeah,
the user
can do that.
yeah, so maybe we can make the user do it and call the, yeah, maybe we could do it in the SDK, make the SDK call the contract to get the number of shares and then pass that in.
And then run the auction on the shares.
Yeah. Another thing we could do is do like a block handler. So make the subgraph recalculate the shares every block.
Yeah, we could do that.
Yeah. We could, because you can make the subgraph call like contract, like call view functions on every block and update your subgraph entities.
That would work.
Yeah. Yeah, I actually found some other issues in the subgraph too. So I want to fix the subgraph before we review it. So we can probably review it like we can do one of the we can do a walkthrough tomorrow of the subgraph.
Okay, sweet.
Okay.
Cool.
Okay, cool. We can wrap this up then. Sounds
Nice,
good.
well done. What are
Sweet.
the main task items? Because we should probably get some of these to do things done before the audit.
Yeah, so the auction stuff, the caching of this stuff is probably the biggest thing, because I think that'll involve like adding Redis or something. Because that does need to be like crash resistant, right?
Yes.
Yeah, so but I think it'll actually be a good idea to do it in Redis, because it's like we don't need to persist it forever.
Yeah, no, I think Redis is the right
Yeah.
tool for this.
Right.
For
Okay.
sure.
And then also the AMM stuff, we're not doing that. The auction, does anything else need to go into auction? We need I guess the SDK side of the auction stuff, which is not in the router. Yeah, the router just needs to respond to auctions, doesn't need to do anything else.
Yeah, and it should probably have that dry run functionality in there.
Yeah, the dry run stuff. Yeah, we can add that pretty easily. Cool.
And then, yeah, just validating the auction that it was prepared with.
Yep. Yeah, exactly. The validation stuff. I think I wrote to-dos for that.
Yeah, you did. All right, sweet.
Cool. All right, sounds good. I'm going to grab some food now, so I'll talk to you guys later.
All right, talk to you in a bit. Bye.
Bye.
Later.